Okay, as you know, we have a lot more students in this class than we were planning on, and not enough teachers. And so we're going to have to make some compromises. And one of those compromises is that instead of having the full tutorial experience where you interact with TAs in small groups of 3 to 4 students, um, you're going to have to interact with me um, through video. And I'm sorry. Best we can do given the circumstances. So this is the first tutorial, and we're going to uh, explore electrostatic interactions today and the idea of charge. And so I've got a couple of cameras set up here to um, both do the worksheet and also to do the exercises that come with this tutorial. But this is my first kick at this can, and so it may work, may not. We'll give it a shot here. So let's try to share my screen. We're gonna share that screen there. Okay. So what you see there is just a stand, and that's where we're going to do our experiments. And then we're going to switch over to a camera here where we're going to actually talk about the tutorial itself. And you should have a copy of this in front of you to fill out as we go through. The first thing we're asked to do is take a piece of sticky tape, and you can try this at home. Just Scotch tape will work just fine. And we want to rub it firmly onto a smooth, unpainted surface. And it's important, if you want to not get in trouble with whoever owns the surface, that you make handles. And let me show you what I mean by that. I take that piece of tape and just fold it over so that I've got a little handle there. And then I'm going to put that right down on and rub it onto the tabletop. Then I'm going to make another one because tape is cheap. I'm going to put that right here. Now, if I rip that up, you see that piece of tape hanging there. And if I bring a pen nearby, what you see is that it's attracted, the piece of tape is attracted to the pen. And if I bring my hand nearby, it's attracted to my hand as well. Indeed, anything I bring nearby seems to attract it. So hold that thought. Okay, I'm going to put this back down and rub it again. Now, the next thing we're asked to do, okay, let's go back and fill this in. describe the behavior of the tape as you bring objects towards it, either a hand or a pen. The tape is attracted to the objects. But now we're asked to make another piece of tape, and lo and behold, we did make two. And we want to bring the second tape towards the first. And so let's try that. Okay, I'm gonna rip up both of these. And now, as I bring these close to each other, what you see is a definite repulsion. Okay. Now, let's go back to our tutorial. They repel each other. Okay. It is important that we keep our hands and other objects away from the tapes. Why is that necessary? Well, we saw up here that my hand and other objects are going to mess with the experiment because the tape is attracted to my hand and to objects like a pen. It seems like we only get this repulsion when we do the same thing to those two pieces of tape. Now, the next thing we're asked is, how does the distance between the tapes affect the interaction between them? Well, let's explore that. So if I look at the tape, as I bring them closer together, the angle increases. So it appears that this repulsion gets stronger as the distance gets shorter. Okay. Gonna get rid of that piece of tape and make another one here. So smaller distance, stronger interaction. Okay, now we're going to do another experiment where we're going to take two of these tapes and put them on top of each other. And we're going to label the one on the bottom with a B and the one on the top with a T. And so let's do that. So what we're going to do is we're going to make these the bottom ones. I'm going to put oh, it's a little bit hard to write on this tape, but that's a definite B. Then I'm going to make some top tapes. I'm going to put this right on top of the bottom tape. And I'm going to label that a T. I'm going to do that again. Label that with a T. And what we're going to do is we're going to rip this up, and then I'm going to touch the tape like this. Let me touch the tape like that. And then what I'm going to do is I'm going to rip these apart very quickly. I'm going to rip them apart. 1, 2, 3. Ah. And as you can see, they're attracted to my hand rather strongly. And they're attracted to each other. So let's get rid of my hand by putting these up here. And we're going to let you see those. Okay, so there's the top one on the right and the bottom one on the left. Now, if I do the same thing to the other set, I'm going to rip them apart. And I was able to keep those from grabbing my hand this time. Now, in this hand, I have the top tape. And if I bring that next to the other top tape, I get a strong repulsion. If I bring that near the bottom tape, I get a strong attraction. A repulsion and an attraction. Now, the other tape is a bottom tape. If I bring that near the other bottom, I get a strong repulsion. Let me see if I can make that more obvious by putting this on the side here. And you see that it's attracted to this one here. So if I bring that there, I get a repulsion. And if I bring it close to the top tape, I get an attraction. Okay. So what did we learn there? Let's talk about that. So if we looked at the interaction between two top tapes, they repel. Two bottom tapes will repel. And a top tape and a bottom tape attract. Okay. Well, let's move on to page 2. We're zipping right along. If I take a it tells us to get an acrylic rod, but what I'm going to use is a rubber rod, And we found in lecture that a rubber rod, when it is rubbed with simulated fur, that it becomes, uh, well, Ben Franklin called it negative charge, and we talked about that in class. And we wish that Ben had done otherwise, but it is what it is. So we're going to charge this negatively by rubbing that on the fur. And then what we'd like to do is see how it interacts with the top tape and the bottom tape. So let's go back to our experiment. This is the bottom tape, and you see that it is being repelled by the rubber rod, whereas the top tape is very much attracted to that rubber rod. Okay, this one is repelled, and this one is attracted. Now, in lecture, we introduced the idea that you've seen before in 8th grade, that like charge repels and opposites attract. So that must mean that this bottom tape must be charged the same as the rubber rod. And if we follow Ben Franklin's naming, that would be negative charge on the rubber rod and on the bottom tape. And that means I must have positive charge on that top tape. So let me go back to my. So it looks like the rubber rod acts the same as the bottom tape. We say that the rod and the tapes are electrically charged when they interact as we have observed. Base your answers to the following questions on the observations we've made so far, not on what you read in a book or what you've been told as you were growing up, but just what we observed. Is it possible that there is only one type of charge? Well, I don't think so. I mean, I saw the bottom tape act a whole lot different than the top tape. And that means that they have to be different. The two top tapes were both treated the exact same way, and the two bottom tapes were both treated exactly the same way. So I would say no. We need at least two types of charge. Now, at this point, I could even argue that we need three types, because my hand or the pen, well, that caused an attraction with both the bottom tape and the top tape. And so maybe that's a third kind of charge. But we're going to find at the end of this tutorial that we can model what's going on with my hand or the pen without creating a whole new flavor of charge. So we're going to say that there's at least two types. Now, by convention, and that's Ben Franklin, a glass rod is said to be positively charged when rubbed with silk. Your instructor will tell you whether your acrylic rod is positively or negatively charged when rubbed with the particular material you're using. the rod I was using was a rubber rod, and it was by definition negative. How do two objects that are positively charged react? They repel. And which tape, top or bottom, has a positive charge? We said that would be the top tape. Okay. So that's the end of the first part. So let's move on. Coulomb's law states that the electric force between 2-point charges acts along a line connecting the 2 points. And by point charge, we mean a charged object that's sufficiently small that it can be treated as if it were all located at a single point. The size of the force, the magnitude of the force on either of the charges, is proportional to the product of the charges, and it's inversely proportional to the square of the distance between the charges. Now, in class, we said that that force, the electric force, was proportional to, we used Q to represent charge, and we used little r to represent the distance between them. So if I had a Q1 and a Q2, and this was the distance r, that would be, we call that Coulomb's law. Now, we're going to start with two positive point charges, a little q and a big Q, where the magnitude of the big Q charge is much, much bigger than the magnitude of the little q charge. And they're held a distance s apart. What would be the direction of the electric force between these? And because they're both positive, they're going to repel each other. And so I would have a force here. If we use our labeling convention, by and on, this would be the force by the big Q on the little q. And this would be a force by the little q on the big Q. Now, which of these forces is bigger? And remember, this charge is a bigger charge. Whatever units we measure charge in, and in lecture we talked about the Coulomb, this one has more coulombs than that little q. And so how do we compare those two forces? Well, if we go back and look at Coulomb's law, the force depends on the product of the two. And so if this is 3 and that's 4, well, if I switch those around, 4 times 3 is the same as 3 times 4. And so the two forces should be exactly the same. And so these are equal. And we can either invoke Coulomb's law, or we can invoke Newton's third law, the most beautiful of all the laws. I can't push on you any harder than you push on me. It's part of the same interaction. By what factor would the magnitude of this electric force on the little charge change if they were moved a distance 2s apart? Well, because this force depends on the distance squared. Twice as far away is going to give me a force that is 1/4 as strong. And 3 times as far away is going to give me a force that's 1/9 as strong. So the force becomes 1/4 as strong. So you see that this force, this Coulomb interaction, drops off very quickly with distance. If you're 4 times as far away, it's 1/16 as far. Now we're going to explore the vector nature of this force. In this case, we start with the situation that we had up here, and we add 2 more charges that are the same size as our big Q in the original situation. And they're all a distance s away, but these are on an arc, part of a circle, off to the side. And we want to consider the following student dialogue concerning the net force, the total force, on the little q. Now, student 1, and you've come to be a little bit skeptical of student 1. Student 1 is often wrong, but let's have an open mind here. He says the net electric force on the little q charge is now 3 times as large as it was before, because there are now 3 positive charges that are pushing on it. Well, remember that this push was along the line connecting the pusher and the pushee. And so that means if I call this charge 1 and this charge 2 and this charge 3, that the force due to 1 is going to be in that direction, and the force due to 3 is going to be in that direction, and the force due to 2 is going to be in that direction. And I didn't draw those very cleverly. Okay. Now, if those were all pointing in the same direction, then I would say that student 1 was correct. But they're not pointing all in the same direction. And so this is not only wrong, but sick and wrong. Let's look now at student 2. Student 2 sometimes gets it right. Student 2 says, I don't think so. The force from the positive charge on the left will cancel the force by the positive charge on the right, and the net electric force will be the same as in part A, namely this right here. Well, that seems wrong, because these 2 forces, if you add them as vectors, they're not going to cancel each other because they're not pointing in opposite directions. So we do not agree with either one. Both are confusing the vector nature of the force. Indicate the direction of the net electric force on the plus Q. Well, if I think of the force by 2 and 3 as having x parts that cancel each other and y parts that add to each other, what I'm going to get is something that is bigger than one force, the force due to charge 1, but in the same direction as the force due to charge 1. Okay, because these X components, these horizontal components, cancel out by symmetry. Okay, so it would be toward the top of the page. What, if anything, can be said about how the magnitude of the net electric force on the plus Q changes when the two are added? It increases. Because the vertical components are adding. Now we've got a little exercise here that we need to rank the force acting on the little charge in these four cases, A, B, C, and D. Now, I hope we can see that that B is greater than A. Well, how do we justify that statement? Well, that's what we did up here. B is just 3 of these guys all in the same place. And so I would be adding 3 contributions, full contributions, all in the same direction. If this were, I'm making up a number here, 5 newtons due to one of these big Qs, then with 3 of these big Qs all pushing in the same direction, I would have a force of 15 newtons on that little charge. And so that's going to be a really big force. We found that when I had these 3 charges along this arc, this part of the circle, that all of these contributions, all of these forces were the same size because the Qs were the same distance away from the little q. But part of the forces left and right canceled out. And so it was only the vertical part that added. And so if I go down here, this contribution is going to be less than B. Well, what about C? Well, I'm going to make a little bit of a change to the drawing. And you know that I have a hard time drawing, but I'm going to draw that circle that we had over here. And so you see that by going from case A to case C, I'm just moving these charges on the left and right further away from the little q. It was up here and here, and we moved them back. And so that means the contributions are going to get smaller from the one on the left and the right. And so it's going to have an even smaller case, and A is going to be bigger than C. Well, what about case D? Well, in case D, I've got 3 Qs here, big Qs, and a negative 3 big Qs there. So why don't you pause the video for a moment and predict how that case D is going to be ranked with the other 3. Where would it fit in that lineup? Okay, I assume that you are back with us, that you've turned the video back on. I hope that you said that D was the biggest of all. Well, let's see why that would be. I know that with just these three Qs here, I'm going to have a contribution that is this big. Remember, we made up numbers and said that that was going to be 15 newtons if that was 15 newtons, right? Well, what if this negative 3Q was at an angle of 90 degrees with respect to this positive 3Q? Well, in that case, I would have a force this way that would also be 15 newtons. And the total force, when I add those two vectors together, would be given by Pythagorean theorem, and that would be the square root of 15 newtons squared plus 15 newtons squared. And if you're good at math, you can see that that's just the square root of 2 times 15 newtons. Well, the square root of 2 is 1.41 times 15 newtons. And if I use my handy calculator, I can't do that in my head. That gives me 21 newtons. Okay, so that's a lot bigger than the others. Now, it wasn't 90 degrees, it was just a little bit less than 90 degrees. And so the answer is going to be a little bit less than 21 newtons, but not much less. Now, the reason that we put it a little bit less than 90 degrees is that in the first edition of this tutorial, it was 90 degrees. And when students went to that, they immediately plugged into Pythagorean theorem and got the answer because they let the math tell them what it was. But as soon as we move that angle to be a little bit less than 90 degrees, suddenly the students couldn't use Pythagorean theorem. They didn't have a mathematical crutch, and so they just tried to use their intuition. And they often would say that, well, this contribution is going to cancel that contribution, and case D would be the smallest of all, when indeed it's the largest of all. So I hope you made that prediction correctly. Well, now we're going to do some experiments to try to explore what happens when the charge is not concentrated in a point, but spread out over a surface. And so what we're going to do is we're going to get rid of these charged pieces of tape, put those in the trash, and we're going to bring down this little ball. Now, what I'm going to do here is I'm going to see if this, oh, you can't see what I'm doing because I'm using the wrong camera. Okay. I have this little ball here, and I'm going to take the rubber rod and I'm going to charge it with the fur. And when I bring it close to that ball, the ball comes towards it. And that's because the ball originally was not charged. It was like my hand. And my hand, remember, was attracted to both the bottom tape and the large tape. And now you see that now that the ball is charged, it's being repelled from that rod. Okay. Now, if I bring it over on this side, you see that it's, oh, my hand's in the way. If I let me put my hand behind. Okay, this is not working well. Let's try it again. Okay. Now you can see the repulsion. If I take that away, let it calm down. I bring this in, and what we find is that it is repelled, since both of these have the same sign of charge on them, both negative, they're repelling each other. And when I put the side of the rod next to the ball is repelled perpendicular to the ball, to the rod. When I put the tip next to it, what I find is that the ball is pushed away radially from the tip. Let me see if I can make that more obvious here. Okay, so let me go back to the tutorial. So, is the ball charged after it touches the rod? Yes. Does it have the same sign charge as the rod or the opposite side sign? The same. And how can I tell they repel each other? Now, if I hold the charged rod horizontally and use the pith ball to explore the region around the rod, you know, let's try that. Let's try that. I'm not sure how this is going to work, but you know what? We're in a physics class. We should experiment. Okay, I'm going to look down on this and I'm going to charge up this. And I'm going to take this off of here. And okay, get that off of here. So if I bring this around, what you see is that near the end, I'm getting the ball is kind of going around in a circle as if it's being pushed radially away from the rod. But along the sides, it's being repelled perpendicular to the rod. And whether I put it on this side or that side, it gets repelled by the rod. Okay, so that worked okay. Now, if we put arrows to represent the force on that pith ball, what we found was that when you were next to the side of the rod, we got forces that were perpendicular to the rod and about the same size. And the further away from the rod, the smaller the force. But when we were near the end of the rod, we were getting something that was more radial, out like this. Okay. So is all of the charge on the rod located at a single point? Is it all at the tip of the rod or at the middle? No. And how I can tell is if I call that force A and I call that force C, force A is about the same as force C. So I must have charge all the way along this rod. And we said it was negative charge because it was a rubber rod. On the basis of the vectors you have drawn, is it appropriate to consider the charged rod as a point charge? No. The point charge would have, the force would be everywhere radial, like that. Okay. Now imagine that two charge rods are held together as shown, and a charged pith ball is placed at point P. Predict whether the rod that's further from point P would exert an electric force on the pith ball. So we've got the two rods, the close one and the far one. And essentially, the far one is behind the front one. And so what we're asking here, we're looking down at a top view. What we're asking here is, are both of these rods pushing on the pith ball, or is it just the closest one? Is the one that is behind the near one shielded some way? Is it because it's behind, it's blocked so that it's not contributing? And we're going to explore that. And the way we're going to explore that may or may not work, but we're going to give it a college try. Okay, I'm going to put this back down here. So what I'm going to do is I'm going to charge up these two rods one at a time. And then I'm going to put these two charge rods next to that pith ball, and you see that there's a strong repulsion. And what I'm going to do is I'm going to leave the near one in place while I remove the far one slowly. And we want to see whether the angle at which that pith ball is hanging stays the same or gets smaller. So as I bring this one away, what we see is that the angle gets smaller. And what that tells us is that both of these rods are exerting a force, even though one is blocking the other, even though one is in front of the other. And so it turns out that all the charge has an effect, and we have to essentially add up, we call that superposition. We add up the contributions of all the charge on the pith ball. And so what we found was both rods are pushing on the pith ball. Okay. Now, we are going to explore this idea of superposition. We're going to pretend that that charged rod is made up of 5 chunks, and each of those chunks are equally charged. If the charge of the whole rod is big Q, then each of those chunks would have 1/5 of that charge. 1/5 of that charge. Now, if I place a pith ball at A, what I'm going to find is that this charge here at 3 is going to repel directly away from 3. And 2 is going to repel directly away from 2. This would be due to 3, and this would be due to 2. Now you notice that I drew that arrow for 2 shorter than the one for 3. Why? Because 2 is further away than 3 from the pith ball when the pith ball is at A. But 4 is the same distance from the pith ball as 2, and so it would give me a contribution that was the same size as the contribution by 2. The contribution by 1 is going to be very short and away from 1. And the contribution by 5 is going to be very short and away from 5. Now, I hope you can see that the contribution in the horizontal direction by 4 cancels the horizontal contribution by 2. 4 has a horizontal contribution to the left, 2 has a contribution to the right. If I were to draw those 2 down here, I'm going to just do it over here. I would have 4 this way and 2 that way. I could think of this as a X part that cancels and a Y that adds. So this would be 4x and this would be 2x. This would be 4y and 2y. So you see that the 4x cancels the 2x, but the 4y adds to the 2y. And so what I get is a total force that is away from the side of the rod. Now, if I look at B, I'm going to have a big contribution due to 5. I'm going to have a smaller contribution due to 4. I'm going to have an even smaller contribution due to 3, an even smaller contribution due to 2, and one that you can barely see due to 1. But they're all pointing in the same direction because they're all pushing away from themselves. And so the net force would just be the sum of these. Okay. So does segment 2 exert a force on the pith ball when the pith ball is placed at point B? Well, yes. We proved that on the previous page. Okay. Now we have student 1 and student 2. So let's see what they're saying. They're talking about these two cases, A and B. With A, we just have the same situation that we had clear back at the beginning of this tutorial on the second page here. And we said that this was, we made up a number. We said that that push was going to be 5 newtons. And so let's go back and remind ourselves that that push we said was 5 newtons. That's a number we made up. Well, now in case B, we take that same big Q and we spread it like peanut butter along the surface of this rod, so that whatever charge I had located right here, I now have spread evenly across this rod. And student 1 says, well, the charged rod and the charged ball have the same charge, plus Q, plus big Q, plus this would be plus Q, big Q, and this is plus big Q. And so student 1 says they're the same distance from the point charge, little q, and so the force on little q is going to be the same in both cases. So student 1 says the force on little q here is going to be 5 newtons again. What do you think? Pause the video and talk about whether you agree with student 1 or not. Okay, I guess you're back on the video. No, of course you don't agree with student 1. He's not only wrong, but sick and wrong. And that's because when we spread that Q across this, this rod, if the total Q is capital Q, well, this is going to be Q over 5, and this is going to be Q over 5, and this is going to be Q over 5, and this is going to be Q over 5, and this is going to be Q over 5. And so the part of the rod that is directly below the little q, it's only got a small fraction of the total charge. And all the other charge is further away from the little q. And more importantly, it's pushing in directions that cancel partially. The horizontal part cancels out, and only the vertical part adds. And so this is wrong because of what we learned up above. Student 2 says, no, in case B, there are charges spread all over the rod. The charge directly below the point charge will exert the same force, 5 newtons, on the ball as case A. The rest of the charge on the rod will make that total force even bigger. He's saying that this charge here is going to give me the same 5 newtons, and then all of this charge is gravy. It's going to give me more. Well, the mistake that he's making is that this charge here directly below the little q is not plus q. It's just going to be plus q divided. You know, if I break this up into 5 chunks, that's just going to be plus q over 5. Now, indeed, I could have broken that rod up into 1,001 chunks if I was really, really bored and had plenty of time. But 5 seems to be plenty to prove my point. So neither student is correct. And so discuss with your partners what errors they are making. So why don't you pause the video again and talk about where student 1 and student 2 are making their mistakes. Okay, we are at the last page. And on the last page, we're going to try to understand why my hand was attracted to both the positive top tape and the negative bottom tape. And what we're going to do is we're going to look at a ball that has been painted with charged paint. And we are painting it with negative paint on the left and positive paint on the right. And when we get that all painted up, we're going to bring some positive charge over here to the left of our ball. Now this could be a positively charged rod, or this could be the top tape, or it could just be something we talked about in class, like a positive charge, like a glass rod. Would the ball be attracted, repelled from, or unaffected by the positive point charge? Well, let's see. We know that like charges repel. So this positive charge is going to repel the right half of the ball. And I'm going to get a repulsive force. This is going to be due to the point charge on the right half. Well, oppositely charged objects attract. And so I'm going to get an attractive force on this side by the point charge on the left side. But the question is, how big should I draw this attractive force? Well, I know we've seen it in the experiments that we've done, that this interaction gets stronger the closer the charges are together. And the left side of this ball is closer to the point charge than the right side of the ball. And we found that dependence on distance was very strong. It depended on the distance squared. And so that means that this left side is going to be attracted much more strongly than the right side is repelled. And when I add those two forces up, I'm going to get a net force that is attractive, a net electrical force on the ball that is attractive. And so I would say that it's attracted. Is my answer consistent with Coulomb's law? Yes. Distance matters. Okay. Now, if I start with a metal ball, that's metal, and I bring a charged piece of tape. Let's bring, in this case, bring the, instead of the tape, let's bring the negative rod. Well, what's that going to do to the charges in the metal ball? Well, we talked about this in lecture. It turns out that the positive charges are fixed in place. They make up the nucleus of the atoms that make up the metal ball. And so they don't go anywhere. They're part of a lattice work. But the negative charges, the electrons, are free in a metal to kind of swim around where they feel most comfortable. And they're going to be repelled by these negative charges on the rubber rod. And so I'm going to get more of these negative charges concentrated over here than over on the left. And so when I look at this metal ball, it starts to look a lot like this ball up here. Except up here, we brought a positive charge, and down here, we're bringing a negative charge. In both cases, we're setting it up such that the ball is polarized. It's got one half that is more charged with one sign of the charge, and the other side that's more charged with the other sign. So in this case, it's positive on the left and negative on the right. Up here, it was negative on the left and positive on the right. But in either case, the force that is acting on the nearer charge is always going to be stronger than the force on the far side. And because the far side is always going to be a repulsive force, I'm always going to get an attraction. So the way we can understand the attraction due to neutral objects is that they get polarized. When they get near a charged tape or a charged rod, we get the electrons moving in the object, the neutral object. The object that's neutral still has the same number of electrons as protons, still the same number of negative charges as positive charges, but they're not in the same place. Because of this polarization, we get a stronger attractive force than we get a repulsive force. And as a result, neutral objects are attracted to anything that's positive or anything that's charged. Here we found that this ball was going to be attracted to the positive point charge. Here we found that the neutral ball was going to be attracted to the negative charge rod. It doesn't matter whether it's a positive charge or a negative charge, a neutral object is going to be attracted. That's the end of this tutorial. I hope that it was useful. Again, this is an experiment. We're just trying to do the best we can with the resources that are available to us. And we're going to be flexible during this semester to try to improve the situation. I'm going to stop sharing my screen, and I'm going to stop the recording.